Hi everyone, welcome to my channel. Today we will discuss about one of the interesting topic, array representation in the memory. As a software engineer, most probably one of the data structure you use frequently is the array. There are known facts related to array data structure. Accessing element at any index takes constant time complexity. Also, once we declare array object and create new array object in the memory, we cannot resize its size. We cannot increase its size or we cannot reduce its size. Before move to main topic, let's quickly refresh our memory and give information about types of memory in the computer. The first type of memory in the computer is called permanent memory. It includes SSD, HDD, or flash memory or other external memories. And it's called permanent because data which lives in this memory, it doesn't depend on active session. Whenever we restart the computer or shut down or open our computer, data still lives there. We don't have any data loss. This storage is out of topic and we will not cover this storage in our video, in this video session. Second type of memory is RAM, or we call it temporary memory. We call it temporary memory because data which lives in this memory is temporary. Simple example. Whenever when you click in your laptop or computer, when you open the photo, in the reality photo itself is located to storage. When you open the photo, that photo is loaded from storage or permanent memory to RAM. Then you are able to interact with that photo. You can zoom in or you can zoom out or you can do any modification. Data still lives in the RAM until you click the save button. And in this case, when you click the save button, data will be saved back in the permanent memory or storage. As we quickly refreshed our memory, let's explore how data represented in the memory. In the computer science, smallest unit of data representation is a bit. Bit represents state in the memory. It can have two states, 0 or 1. For example, 1 byte equals 8 bit. That means in 1 byte memory, we can represent 2 power 8 states. That equals 256 states. If we take a look at the example over the numbers, 1 byte information can store this interval starting from 0 between 2 power 8 minus 1. That equals 0 between 255. We exclude 1 because as we start counting from 0, we have to exclude 1 from last position. This is the smallest number which equals 0 for this interval. This is the largest number which equals 255 for this interval. But in the practice, we usually use signed integers. That means integers or any numbers long or byte, it can be negative or positive. In case of signed number, 1 byte can be represented like this, and leftmost bit is used to store sign information. For negative numbers, we mark 1 as a sign. For positive numbers, 0 marked as a sign. For this interval, this is the smallest number, which equals negative 128, and this is the largest number, which equals largest positive number, which equals 127. Still, you see it's 27. We exclude 1 because this interval also includes information 0. As we have seen how data binary representation looks like, now let's turn our attention to how memory model looks like. For example, for 1 megabyte, we have 1024 multiply 1024 bytes. That equals 1,000,000 28,576 bytes. Let's see how 1 megabyte look like in the memory. You can see all these squares are memory block, and each memory block is addressed, and its address are represented in the hexadecimal format. They are sequential, and each byte is addressable in the memory. There is a reason behind of it why each byte is addressable in the memory, not each bit. Because CPU, aka Central Processing Unit, when interacts with the memory, it reads data byte by byte. For 1 megabyte memory, this is the first address, this is the last address. But modern computers, laptops, has many more bytes by comparing to past, and it's measured with gigabytes or even terabytes. For example, my laptop has 16 gigabytes. That means my laptop has 16 multiply 1024 multiply 1024 multiply 1024 bytes in overall. As we have seen how memory model looks like, let me break down further, and let's see when we declare variable and assign a value, how that value represented in the memory. This is a variable declaration in the Java programming language. Variable x in type of integer assigned a value to 7. Integer takes 4 bytes in the memory, and for 7 in the 4 byte memory representation, binary representation would look like this. And these 4 bytes in the memory would be located like this. And you can see each byte located in the memory and every byte located in the sequentially. Here we have one important point, and this is base address. Base address is always first byte. This is important for our reference, because when we have access to x value, when we retrieve x value, we need to know information about base address. When we know start location, we know integer types takes 4 bytes in the memory, and then we will read 4 sequential bytes, and in the end result will be back to 7. Let's unpack a little more, and it's time to see how array elements are represented in the memory. This is an array example which is written in the Java programming language with size of 3, and there are 3 elements in the arrays, and type is integer, and each integer takes 4 bytes in the memory. That means when we create this array, 3 multiply 4, 12 bytes are allocated in the memory for this array. Let's see for each element how binary representation looks like. And let's see how this binary located in the memory. This is a memory representation for each array element. They are located in the memory, and for each element bytes are sequential, and this is the element at index 0, element at index 1, element at index 2, and they are located in the contiguous blocks. And again this base address, it's important for this reference, because when we access element at any index, we need to know information about starting point, base address. Base address is always first byte. Now it's time to see what happens when we access element at any index, how it's calculated, which formula is used. And this formula is used to calculate memory address starting address for element at any index. This is base address, this is index, multiply type size in bytes. In our case, type size is integer. It takes 4 bytes in the memory. Let's take a look at the example and let's calculate element at index 0. And this is base address. Base address reference always are informed about base address starting point of memory location. This is base address, this is index for index 0 and multiply 4. 0 multiply 4 and equals 0. That means starting point will be this address. And starting from this address, when we access element at index 0, starting from this address, 4 sequential byte will be read at in the result. It will give us 3. At the same manner, and other index elements are accessed. Now let's back the question in the beginning of the video which we were asked. What's the reason we cannot resize the array once it's declared and created array object in the memory? We are not able to increase its size or reduce its size. The reason is that there is no guarantee that after created array object in the memory, the rest of contiguous blocks will be taken or not. There is no guarantee that this block is already taken by another process or it's empty. Technically, by using low-level programming language, you can implement your own custom array core data structure. You can make it extendable and you can make it resizable, but it's not recommended, because in case this block is taken, your data structure will not be able to resizable and it will lead to inconsistencies. I hope you have all answer for your question which we were asked in the beginning of the video. Why accessing element at any index takes constant time complexity, because every element are located in the contiguous block, and this formula is used to access an element at any index inverse of constant time complexity. And why we cannot resize array object in the memory once we declared, because there is no guarantee that these contiguous blocks are taken by another process or not. You may wonder, what about string array? Because its string element in the array can be in different size. Let's remember that string itself also object like other object type. And when we declare string array, we don't store string itself in the array block. We store reference in the array. That's the reason we are able to declare and use string array. And at the same manner, all other object types work. You may ask question, what about characters? And depending on its type, ASCII or Unicode, and ASCII takes 1 byte in the memory. You can imagine a character mapping between decimal value and character itself. When we store character value in the memory, actually not character itself stored in the memory. It's the decimal binary representation stored in the memory. When we access character in the memory, we access its decimal value, then it's converted to character based on that mapping. Now you have deep understanding about array data structure, how array elements are allocated represented in the memory and how memory model works when we declare variable, how it is represented in the memory. In the next video, we will implement our custom dynamic array and as known an array list, and after watching that video you will be able to implement your own custom list in a couple of minutes. Please don't forget to subscribe my channel and like the video. You cannot imagine how important for me and how it motivates for me create more content like this. And also please don't hesitate to share your ideas and share your feedback in the comment section. Thank you very much. See you.